Greetings. This is section 8.3. I'm going to do this video in 3 parts. Well, I'm going to do this section with 3 videos. 1 power series example per video because the examples are so long. To that end, I'm going to skip over this first page, which is some fluff that I would talk about if we were in class, and move on to the definition of an ordinary point versus a singular point. The method we're going to use today for solving differential equations with power series only works around an ordinary point. And so the definition of an ordinary point is up here. If we have a differential equation in this form, then we need P and Q to be analytic at x naught. Now that just means very nice. And so that's a little bit vague, but to make it more specific, if P and Q are rational functions, then we don't want to divide by 0. So those are going to be the bad spots. Those will be the singular points. So in these examples here, the first thing we need to do is write the differential equation in the form where the coefficient of y double prime is 1. So I need to divide through by x here. So we get minus xy prime plus 5 over xy is 0. So P of x is negative x, and Q of x is 5 over x. So my singular points are going to be the values of x where either P is undefined or Q is undefined or both. So P is fine, but Q, I see there's going to be a problem when x is 0, so I have a singular point, and that's at x equals 0. All right, for the next one, again, I divide through by x minus 1, y double prime plus x plus 2 over x plus 3, x minus 1, y prime plus sine x over x minus 1, y equals 0. So my P is x plus 2 over x plus 3, x minus 1, and my Q is sine x over x minus 1. My singular points, I'll have 2 of them. P has problems at negative 3 and at 1, and Q has a problem at 1. So those are my singular points. So again, the method we're using today will not work around singular points. It will only work around ordinary points. But all the examples will have an ordinary point. And so here's a theorem telling us what solutions look like and that we can actually find 2 linearly independent solutions around an ordinary point. And just let me show you how this works with an example. I think it will be easier. We're going to assume that a solution looks like this. 0 to infinity Cn x to the n. Okay, because the ordinary point is x equals 0, so we're finding a power series solution expanded around x equals 0. So that's y. And then y prime, remember how to take the derivative and second derivative of a power series. This is going to start at 1. This is from section 8.2. You bring the n down, Cn is constant, and then subtract 1 from the exponent. And then y double prime, remember for y double prime we're going to start at 2 because the n equals 0 and the n equal 1 term are 0, so we start at 2. We bring the exponent down, so n times n minus 1 Cn, and subtract 1 from the exponent. So all your power series problems will start with that step. Y prime and y double prime. They'll all look identical to that. What will be different is the equation you plug those functions into. So in this case, we're plugging into this differential equation. So y double prime is the sum, n equal 2 to infinity, of n minus 1, Cn, x to the n minus 2. And then I want to add on x times y. Y is n equals 0 to infinity Cn x to the n. And now remember, this is an equation, so when you send me your work on the next test, which you will, I want to see that equals 0 there. distribute. Okay, I need to bring that x in. There's nothing to do with the first expression. N equal 2 to infinity, so I'm just going to copy that down again. N minus 1 Cn x to the n minus 2 plus, okay, this next guy, the new exponent will be n plus 1, because x to the n times x is x to the n plus 1. So n equals 0 to infinity Cn x to the n plus 1, and that equals 0. Reindex. So each of these summations needs to be written in terms of x to the n, not x to the n minus 2 or x to the n plus 1. So for this first one, in order to make this an n, I need to add 2. So everywhere in the formula, I'm going to add 2 to n. So n plus 2, n plus 1, Cn plus 2, x to the n. And remember, if you add 2 in the formula, you need to subtract 2 where you start. So that'll start at 0. Then I add on some. This one I need to subtract 1. So I'm going to add 1 down here. This one will start at 1, and it'll be Cn minus 1, x to the n. And again, that equals 0. Combine, meaning I want to write this now as a single summation, single power series. So I need to start at the highest value of n. So this one starts at 1, this one starts at 0. I need to start them both at 1, which means I need to cull off the 0 term for this first power series. The 0 term is 2c2. All right, and then I'll go sum n equals 1 to infinity, and I'm going to add the coefficients, and I'll have a single x to the n equals 0 there. So I add the coefficients. Inside I'll have n plus 2, n plus 1, Cn plus 2, plus Cn minus 1. So we've done all these steps before, they just weren't in equations, it wasn't equal 0. So now we're going to take it further, recurrence relations. We set all coefficients equal to 0. So this first coefficient, 2c2, is 0. So now I know c2 is 0. So that's one of the recurrence relations. And the main one I get from setting this equal to 0. So I have, make this a little bigger, n plus 2, n plus 1, Cn plus 2 plus Cn minus 1 equals 0. Solve that for the larger value, the larger index. So I want to solve for Cn plus 2 in terms of Cn minus 1. So I bring the Cn minus 1 over, and I'll have a negative 1 over, and then divide by this coefficient. I'll have negative 1 over n plus 2, n plus 1, Cn minus 1. And I want to see that in your work. That's really important. That's the recurrence relation, and that's valid for, look at where the summation starts. If that started at 2, I'd say n equal 2, 3, 4. That starts at 1, so 1, 2, 3, dot, dot, dot. Now, the goal is to find all the Cn's in terms of C0 and C1. We have to go up to C5. Okay, so when n is 1, I have C3 equals, I'm reading this equation and putting 1 in for n. I have C3 is negative 1 over 6 C0. All right, and there's nothing to do after that. When n is 2, I have C4 equals negative 1 over 12 C1. Okay, and then when n is 3, I have C5 is 3 plus 2 is 5. 5 times 4 is 4, 20. Negative 1 over 20. C2. Now I have to write everything in terms of C0 and C1. So up above, I see that C2 is 0. So that's 0. Now I only have to go up to C5, but just to show you the pattern, I did one more. When n is 4, I get C6 is negative 1 over 30 C3, but C3 is negative 1 6 C0. So I plug that in, and then I simplify, and I get 1 over 180 C0. And if I had to find, terms up to degree 7, I could go n equal, 5, and then that would give me C7. And I'd have to simplify and write it in terms of C1 and C0. Okay, now what do you do with these C's? Well, it's important not to skip step 6, which everyone skips because it seems unimportant, but it really is very helpful. This was all predicated on the fact that our solution looks like this. Y is C0 plus C1x plus C2x squared, blah, blah, blah. So I'm going to plug in to this equation all the C's and write everything in terms of C0 and C1. So C0 is C0, C1 is C1. But C2, up above, you can see C2 is 0. So I've got 0x squared. No, you don't have to write 0x squared, but I did just so you can see why that term is missing. Plus C3x cubed. C3 is negative 1 6 C0. So this will be minus 1 6 C0 x cubed. Then I got my C4 x to the 4th. C4 is negative 1 12th C1, and that's x to the 4th. And then C5 is 0. And then if you wanted, you could do the next term, 1 over 180 C0 x to the 6, dot, dot, dot. We're only going up to the degree 5. All right, so now I've got an infinitely long polynomial, and the only two constants are C0 and C1, so I want to separate this out. I'm going to have two solutions. Well, I have one solution, which is the sum. So my big solution I can write as C0 y1 plus C1 y2. And my y1 is the polynomial I get when I factor out a C0, and I look, so up above here, if I factor out a C0, I want all the C0 terms. So I'm going to get 1, and then the next term involving C0 minus 1 6th x cubed. And then the next one involving C0 is 1 over 180 x to the 6. I don't need that term because I only had to go up to 5, but I'm just putting it there so you can see the pattern. And then my C1 terms are, okay, I've got an x, and then minus 1 12th x to the 4th, and then that's it. So plus dot, dot, dot. All right, now your text is going to want you to use, I believe, A0 and A1 rather than C0 and C1, and it will tell you how high to go. Like it'll say include terms up to degree 3, or in this case we did up to degree 5. So in the next video, I will do this initial value problem with you. You might want to just try it on your own without me, because you can certainly do it at this point, and then check into the next video to see how you did. The only thing different about this one is that after you solve for y1 and y2, you're going to have initial conditions which will allow you to find C0 and find C1.